Okay, hi everyone. So I have been doing some science Q&As for kids and others for the last several weeks, which I've had a lot of fun with. I hope people have enjoyed them. Um, I have kept on talking about this project about fundamental physics that I've been doing for the last several months and how exciting it is. Well, this week we actually have launched our project and started talking about what we figured out about how fundamental physics works. And I thought I would try and give kind of an introduction to what we've done that doesn't involve a lot of technical stuff. We just finished a working session for our project that didn't go quite as well as I'd hoped. That was full of complicated technical terminology and so on, none of which should occur here. Okay, so what are we trying to do? We are trying to make a model for how the universe works. And we're trying to figure out if we can essentially make a way of describing everything that happens in the universe. So I actually just started kind of making some notes that we can send out that will be kind of an introduction to what we're trying to do. Okay, so what is the universe made of? Well, you probably know that pretty much everything around us is made of atoms. There are some exceptions, like light is made of photons, for example. But mostly the things that are like matter, the things we can sort of pick up and do things with, made of atoms. What are atoms made of? Well, atoms have a nucleus made with protons and neutrons, and then they have electrons. And so atoms are basically protons, neutrons, and electrons. So you say, well, what are those made of? Well, protons and neutrons we've known for about close to 50 years now that they're made of things called quarks and gluons. And electrons, we don't know what they're made of. So far as we know, electrons aren't made of anything. So far as we know, or have known in the past, electrons are sort of the end of the line. They're just an electron. There's nothing inside an electron. Electron is just like a point. It's not, it has no extent. It doesn't have anything inside it. And same thing we believed about quarks and gluons, for example, that they're just point things, kind of end of the line, nothing inside them. Well, so one of the things that's coming out of this theory of physics is that we think we know what is inside electrons. We think we know what electrons are made of, so to speak. So the question, the sort of the big question that we're interested in is, what are things made of at the lowest level? And I had one graphic here that I thought might be interesting to see, which is kind of let me share this for a second. Okay, actually, you know what I'm going to do? I'm going to move that and put this graphic here. Hold on one second. Okay, so this is just a graphic to show sort of orders of magnitude of lengths. So we can think of this this is multiples of 10 in, let's say, meters. So, a person is maybe 5 feet tall, a couple of meters tall. The Earth is maybe 1 million meters, about 10 million meters across. And so that would be, so we can say if something is 1 meter across, we'll say that's 0 here. If it's 10 meters across, we'll say that's 1. If it's 10 times 10 meters across, it's 100 meters across. We would say it was a 2 here, and so on. So we can kind of mark the relative sizes of things, always going up by multiples of 10. So each number here, so 10 here means 10 multiples of 10. So there's sort of a size of a person, size of the Earth, size of the solar system, size of the galaxy, size of the whole universe. So that's kind of going up in sizes. So we can see kind of the in each time we're going up by a factor of 10. So we get 20 multiples of 10, we're getting up. The size of the galaxy is like 10 to 10 times 10 times 10 times 10 times 10, 21 times roughly meters. And the universe is 26 multiples of 10, multiplying by 10 of a meter. Or you can say that in terms of millions and trillions and so on. So let's see if I can count it off on my fingers. It would be the universe is about a trillion. It's about 100 trillion meters across. So that's that's kind of the sizes of big things. When we get down to the size of small things, we're looking at a small fraction of a meter. So an atom is not 1/10 of a meter, but it's 1/10 of 1/10 of 1/10 of 1/10, 10 times. So we could also say it is it's a little bit more, it's not quite as small as a trillionth of a meter across. And a proton is about 100,000 times smaller than an atom. And so that gives a sense of the size of a proton. The best sort of microscopes we have, which are these giant particle accelerators that are many kilometers, many miles in circumference, those can be thought of as kind of giant microscopes. The best kind of giant microscopes we have reach down to about maybe a millionth the size of a proton. So that's as far as we can kind of resolve how big things might be. Well, according to this theory of ours, electrons are that much smaller than protons and the limit of resolution that we have right now. And what we'll talk about in a minute is the very, very, very smallest lengths one can imagine are down even smaller than that. But okay, so the goal of this project is to try to understand what is the universe made of at the very, very smallest scales. And as I say, we know, most things are made of atoms. Atoms have protons and neutrons. Protons and neutrons have quarks and gluons. And atoms also contain electrons. But those have been the end of the line. We don't know what those are made of. So we're interested, what are those made of? And how does that all work? So the thing that is sort of a big piece of figuring that out is a weird question, which is, what is space made of? So what do I mean by space? I mean what we move around in. I don't mean space as in outer space here. I just mean what we kind of move around in when we exist. So, space for us is three-dimensional, which means we can move forwards, backwards, left, right, up, down. Each one of those directions is a dimension. And in our space, there are 3 dimensions. And that's, we say we sort of live in 3-dimensional space. Okay, so big question is if we're moving around in space, can we move, if we just move a tiny distance, can we move as tiny a distance as we want, or is there some limit? Well, you might say, well, I'm looking at, let's imagine you're looking at your mouse on your computer screen. You might ask the question, can I move my mouse an arbitrarily small distance? Can I just move my mouse just from there to someplace that's incredibly close, but not the same place? Well, computer screens have pixels on them. So if we sort of magnified it, what we'd find is that our mouse pointer looks like this. Our mouse pointer, the tip of our mouse pointer that's saying where we are is not, we can't put it absolutely anywhere. It has to land on a particular pixel on our screen. So in other words, the space of a computer screen is not, we can't just move an arbitrarily small distance on our computer screen. So the big question is, for space in the universe, is it like our computer screen or not? In other words, if we wanted to move something an incredibly, incredibly tiny distance in our actual universe, would we find out that it was kind of in these, would we find out that the universe was sort of made of pixels and we couldn't move that we couldn't move an arbitrarily small distance, we had to move sort of pixel by pixel or not? Well, I don't think the universe is made in a way that's sort of like an arrangement of pixels, but I think it is something where it is sort of a set of discrete points. You know, when you learn geometry, for example, if you learn geometry, geometry kind of assumes that space is continuous. It assumes that there can be, when you put down that point in geometry, you can have 2 points that are as close as you want in geometry. You never have to say, oh, whoops, those points have to be a certain distance apart because they have to land on, if they're not the same point, they have to land on different pixels or something. You're in standard geometry, as one learns it in school or as mathematicians study it, in standard geometry, space is continuous. So that's been kind of the view about how physics works since forever, that space is continuous. It's also, when you learn calculus, calculus is all about studying how things work when there are infinitesimally small changes in things. And that's kind of the idea there. Okay, so one of the big things in this theory of ours is the idea that space is not, in fact, continuous like that. Space is discrete, but not like pixels. It's a slightly more complicated story. So let me tell you what the story is. So the idea is that what space consists of is just a bunch of points, but instead of the points being arranged like pixels on a screen, we just say they're points. They're just little points here, and we could give them numbers. It doesn't really matter. We could give them names. And all we say about these points is how they're connected to each other. We could take those points and we could arrange them differently, and we're just making sure that everything's connected the same way as it was connected before. So 1 is connected to 14. We see here 1 is connected to 14. We're not saying how the things are laid out. We're just saying what's connected to what. So, you know, in an analogy, like you could say 1 is a person, you know, I don't know, named Jane or something. And, you know, Jane is friends with John. And so these points on this graph could be who's friends with who. And we can define, you know, that this graph is telling us what the network of friendships is. You know, person 1 is friends with person 14. Person 1 is also friends with person 12. Person 12 is friends with person 14 as well. So this is like a network of, that you can think of this like a network of, for example, friends. Now, we could say, when we draw this network, we could say, and we're going to draw it so that every person is at the position of where their house is, in physically laid out, sort of geographically laid out. And then it might be that this is sort of where you might lay this out according to sort of where these people live, so to speak. But you might also just say abstractly, person such and such is friends with person such and such. You're not going to say anything about where they live. So our view, and it's a very weird sounding thing, of what points in space are like, it's more like the friends thing than it's like the where they live thing. It's like for every point, we know what points it is directly friends with, so to speak, what points it's directly connected to, but we don't know. We're not saying where those things are in sort of we're not predefining where they are in space, so to speak. We're just saying there are a bunch of points, a big bag of points, and space is made up from these points, and all we know about these points is how they're connected to each other. So we can say, for example, if we want to know in sort of friend, you know, in the friend network, we want to know, can we get from person or point number 1 to person or point number 7 here? We can see there's a chain of points, friends, that it goes through to 1 to 14 to 13 to 16 to 7. We can get there. You know, we want to go from 4 to 13, we can go chunk like that, and so on. Doesn't matter how we've laid this out. We notice here we go 1, 14, 13, 16, 7. I had a different layout for the graph up here. What did I do? Oops, I closed that up. Sorry. Here, let me take that here. That's the code that made that graph. Let me close it up like that. Okay, so here I said I'm getting from 1 to 7. Do the same thing here. I can get from 1 to 7, but now it happens that 1 and 7 are placed differently when we draw this graph, but we can still see the path 1, 14, 13, 16, 7, still the same path. Okay, so that's the so the idea is that space is just made from this kind of bag of points, and all we know about those points is how they're connected. So let me show you a sort of slightly more realistic version. This is kind of a version of the very, 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 very beginning of the universe, so to speak, according to this theory. At the very, very, very beginning of this universe, there weren't very many points, and gradually, not so, there progressively ended up being more and more and more points. And so this might be the representation of the universe in terms of their points here, and they're connected to other points a very tiny, tiny amount of time after the beginning of the universe. And so, you know, we might get something where after a while, the structure of our little tiny universe might be something like this. And again, these dots represent points in space, and all we know is how the points are connected to each other. And by the way, I think I wrote out, I wrote out how many steps the universe might have gone through. And in terms of trillions, it's that many steps. So this was after 10 steps to get to our actual universe with you and me in it and so on. It's that many steps, perhaps, that you have to go. So after it's gone that many steps, the number of these points that would exist in the universe might be something like this. So a really, really large number of these points. But it would start in a way that's a bit like this. So I'm not sure, are people following this at all? Let's see whether people, there's some slightly technical questions here. Definitely. Okay. Well, so let me let me go on and try and explain a little bit more about so the view of space is, it's not like pixels on the screen, but it's like points that just know who they're connected to. That's everything that one sort of knows to define how the universe works. So for example, we can let's talk about how we would reproduce kind of things we know about the universe. So let's imagine that our points were arranged just like this. So every point just has 4 neighbors here. It's just on a so it just looks like this. But remember, it doesn't matter where these points, where we lay these points down. All we know is this point is neighbors with, is connected to this point and so on. But we might reasonably think, if we had a version of this where we had more and more and more points, we might reasonably think this is kind of like, it's like a piece of fabric or something. It's like just a 2-dimensional thing, because we can move here. We can always move to the left and right. We can move up and down here. So we can think of this is like one of our graphs where in some sense we just have a bunch of points, but it's pretty clear that this set of points is arranged in such a way that it's like having a sort of a piece of space that has 2 dimensions. So someone's asking, how many dimensions does one point have? 0 dimensions. Okay, so in this, so we can have, this is like a 2-dimensional thing. We can move up, down, left, right. This would be like a 1-dimensional thing, because we can only move left, right. We can't move up, down. Okay. Well, now we can start saying, what about other dimensions? Well, let's take it a sort of simpler case. We can say this is like a two-dimensional thing. It's a square, looks like a square. We're not thinking about what's inside it. We're just thinking about these points, and we're saying every point we can kind of move to this neighbor and we can move to this neighbor. So this is like 2 dimensions. We can move to the left, we can move down. That's like an ordinary square. If we draw something like this, this is like a cube, sort of drawn in perspective, where every point has 3 neighbors that correspond to the 3 dimensions in space. That's what a 3-dimensional, one of these graphs, one of these sort of collections of points that's kind of like it's in 3 dimensions would be. And we can do the same thing if we want to. We can do it in 4 dimensions. And so we can have the same type of thing, but here it's harder to draw because we're trying to sort of squash it. We're trying to kind of, just like here, we're drawing a 3-dimensional cube in 2 dimensions. So we have to like draw it with perspective and so on. Here we're trying to draw a 4-dimensional cube in 2 dimensions, and that's a bit more challenging, but we can kind of see something about why it's 4-dimensional because every point here has 4 neighbors and so on. So in one of the things that's really funky in our model of the universe is when we have space made from things like this, we can say that sometimes the thing will behave like it's 3-dimensional space, sometimes it might behave like it's 2.9-dimensional space. It doesn't have to be an integer number of dimensions, it doesn't have to be a whole number of dimensions. And that's kind of a funky thing, and we can talk about what that means. But for now, the whole point is that when you have enough points here, the thing can behave like like your computer screen looks like you can draw anything on it, but actually it's made of pixels. So the idea is that in physical space in the universe, you can kind of move, but you can only move sort of from point to point. You can't sort of move anyway. You can only move from a point to the point it's connected to, and so on. And so the it's kind of like when you have any material, I don't know, like water, for example. You know, you have water, and it seems like it's a continuous thing. It seems like I could take this water and I could take a little tiny lump of the water. I could take, you know, I don't know how many cubic centimeters of water there are in this bottle, but I could start subdividing and subdividing and subdividing, and I eventually have a trillionth of a cubic centimeter of water, or a trillionth of a cubic centimeter of water. And you might think I can just keep subdividing it forever. You could just have smaller and smaller amounts of water, smaller and smaller volumes. But actually, it's not true, because eventually you'll get down to the point where you just have one atom or one molecule of water, and then you can't subdivide anymore. And so what has been thought in the past is that with space, you can just keep subdividing forever. There'll never be a limit. You can just keep making smaller and smaller regions of space, and there'll never be a limit. But with our theory, that's not the case. Instead, eventually you get down to the point where you just got one of these points, and then you can't subdivide anymore. Now, these particular, these in this network, this network corresponds to a very, 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 very fine space is still the little sort of the minimum distance in space is still really, really tiny, really incredibly tiny compared to anything we know. And that's why we've never noticed that space isn't continuous. Okay, people are asking all kinds of complicated questions about black holes and things. I'm certainly I'm happy to talk about that, but let's I'm trying to get some sense of whether people are following so far what I'm saying. So the big idea so far is space is not continuous. You eventually, if you go down, look down, finer and finer and finer and finer detail, eventually you'll find out space is made of discrete points, just like you would find out that water is made of discrete molecules, space is made of discrete points, and we're saying something about how those discrete points relate to each other. And so that's kind of the idea of go down to the smallest scales. That's what space is. Now, okay, here's the next really weird idea. The question is, okay, in the universe, it's all well and good to say what it means to be moving left, right, up, down, et cetera, et cetera, et cetera. But there are all these things in space, like us, for example. There are all these atoms that exist in space. What are those things? So here's another weird idea of this theory. The idea is everything is made of space. That essentially what's happening is that, well, let's take an example here. We might have, in a very, very, very simple example, we might have something where space is just like there might be this very simple kind of two-dimensional version of space, just made up of these points. This is how the points are connected, and so on and so on and so on. Okay, but imagine that's sort of what ordinary space is. But imagine that there's sort of a little extra bit in space. So ignore the fact that these are colored red. Doesn't matter. All that matters is that there are these extra connections that exist. And the idea is that those extra connections are representing a thing in space. There's sort of this background of space. Space is just these connections between points, but there are special sort of arrangements of connections between points. And those special arrangements of connections between points correspond eventually to things like electrons and atoms and so on. So the idea is there's sort of what space normally is like, and there's kind of the special, notable, typically rather long-lasting structures in space that are just formed from different connections in space. Still space, but it's just different connections in space. And we interpret those different connections in space as being all the things that we know about in the universe, all the matter, all the atoms and so on in the universe. It's a very elegant idea, because it means you don't have to say, oh, in the universe you've got some of this and that and that and that and that. It's all just space. And what we're seeing is just different features of space. Okay, so how so that's kind of the idea is space is discrete. Space is made from this kind of network that just says how the points in space are connected to each other. Details of how those connections work represent all the things that we know exist in space. So let me try and give you a little bit of sort of intuition about how things like that work. And I want to talk a little bit about one of the sort of surprising things. Well, okay, so actually there are different things to talk about. One question is, okay, so if space and everything is this big network, where did the network come from? How did the network get made? Well, so this is kind of an example of that. I showed this before. This is sort of how the network can grow from this very minimal network with just 3 points in it to add more points and more points and more points. And gradually it's growing a network with more and more and more points. And the way it works is let's see if I can pull that up. There's just a rule that says when you have a network that has a particular form, you add points to it in such and such a way. And when you apply that rule over and over again, that's what builds up this bigger and bigger network. So essentially what's being said is, what happens in the universe is just we have this rule that says how to turn, let me actually find the rule for this particular network. Hold on 1 second here. Have to open this up, show you the actual code. I think we can probably do this. Oops. that was a mistake. There we go. Okay, so that's the rule that was used to grow that network. It just says whenever we have an arrangement of points that looks like this, and there are arrows on here, which you don't have to worry too much about, but whenever you have a arrangement of points that looks like this, replace it by an arrangement of points that looks like that. So very simple rule, just gets applied over and over again. When you do that, you'll eventually build up this kind of complicated thing here. So kind of the notion is, the way the universe works is, it's just applying a rule like that. It won't be this particular rule, but we don't know what the actual rule is, but a rule a bit like this, and it's just applying it over and over and over again, trillions and trillions and trillions and trillions of times. And that and that at the very beginning of the universe, one might start from just something like this, and over time, it would build up to include everything that we now know exists in the universe. So that's kind of the idea. And it's a very, but this notion that you could have a very, very simple rule, and it could build up this very complicated thing that is our universe, that's a really weird thing. And that's something that is very surprising. You might think, gosh, if you have a simple rule like this, how could it possibly do anything other than make something really quite simple? Well, let me show you something that I discovered a long time ago that kind of started giving me intuition about why that wasn't the case. So let me show you an example here. So this is going to be a rule, hold on one second here. This is going to be a rule that is a rule not for points connected in a network. It's going to be a rule for more like something like pixels, where you just have a line of black and white cells, and each cell is either black or white, okay? And this particular rule is going to tell us, based on the colors of these cells, pixels, whatever you want to call them, it's saying, for example, if there's a black pixel and there's a white pixel to its left and right, make the pixel underneath be black, okay? So we can go ahead and do this. Let me just make this, let's do something like this. Okay, so what this is doing is it's saying, I'm going to use this rule up here, and I'm going to, at every place in this picture, we're going to just look. This is white, white, black here. And we want to know what will the color of the center cell underneath that be on the next step. So we just look it up. What's white, white, black? So white, white, black, the answer for the next cell will be black. Okay, I'm going to change the rule a bit. Say it's this rule here. So this rule, I changed it so that now when there's a black cell with two white cells around it, the cell in the middle goes black. So we try that there, and we get this kind of checkerboard thing, okay? So, and you can do this. It's kind of fun, I think. Well, I haven't done very many of these by hand myself, but you can get a piece of squared paper or something. You can go follow these rules yourself. You can say the cell will become black whenever it has any colors above it other than all white or white, black, white. Then you get this pattern here, okay? So you might then say, as I did a long time ago, if you've got rules like this, you'll always get, if the rule is sufficiently simple, you'll always get a very simple pattern. Let me show you another rule here. There's another rule. If you work out what this rule says, it says, if either the left cell or the right cell is black, make the new cell be black. But if they're both black, make it be white. That case there. Okay, so let's see what that one does. So that one makes this kind of elaborate looking pattern. We can keep going a bit longer. Let's say we go for 400 steps, get rid of the mesh because it'll just make a big mess. And we get that picture there. So in other words, even though the rule was really simple, it's this very simple rule up here, we managed to make a pattern that was still pretty regular, but it's nevertheless a much more intricate looking pattern. This particular pattern, it's a nested pattern because each piece of the pattern is like a small copy of the whole pattern. It's kind of lots of patterns nested inside each other, also called a fractal pattern sometimes. Okay, so now the question is, what is it always the case that, oops, I need to save this somewhere. What happens if you pick a different rule? Okay, so my all-time favorite is you can represent it as a number. This is that's that number in base 2 there. So this is my all-time favorite. You started off from just one black cell at the top there, and it seems to be doing kind of complicated things. Keep running it for a while longer, and by golly, it's doing complicated things. It's a bit of regularity in this rule, but mostly it just seems to be doing really complicated stuff. So this, and by the way, I want to emphasize the way we make this pattern. You can do it yourself. You can take this set of rules here, and at every single cell, you're just using the exact same set of rules. No difference. That cell, you determine it by this set of rules. This one down here, you determine it by that set of rules, and so on. Every cell, you're just determining it by the same set of rules. Okay. So the big surprise is that even though these rules are really simple, even though the rules that we completely know what this pattern is going to be, we just follow the rule, it'll tell us what the pattern is going to be. It is still, we can get this really complicated pattern. There's another feature of this pattern that's kind of important, which is you might say, gosh, somebody gives you the exercise, find out what color the center cell will be here after 1,000 steps. Super boring exercise, because you might say, I'm going to be really clever. I'm going to use some kind of fancy math, and I'm just going to figure out the answer. I'm not going to go do that terrible exercise. If you wanted to get to 1,000 steps down here, you'd actually have to fill in 1,000,000 cells altogether. I don't want to do that, fill in all those million cells. I just want to use some fancy math method and just work out what the answer will be. I mean, I might comment that if we looked at something like this, we could get clever and use some fancy mathematical method to work out what the answer is going to be. Actually, if you're curious, down here, down the center of this, there's a black cell at every power of 2 number of steps. So that's a place where we can kind of use a math fact to work out what the answer will be, even after a very, very, very long time, without having to follow every step. In this rule, one of the features of this thing is that I think it has something that I call computational irreducibility. When you try to compute what the answer will be, you can't reduce how much effort you have to put in. To work out the answer, you just have to follow each step and see what's going to happen. It's irreducible in that sense. So this so there's this sort of really big surprise. I mean, I discovered this back in, well, basically this particular thing in 1984, which, assuming there are young folk on the stream, is an infinite time ago. But this fact that even though the rules can be simple, the results of what you get can be really complicated. Okay, and that's the core fact that makes it conceivable that there could be a rule for the universe that's simple, like that one I showed you before for how networks are grown, that if you just applied it over and over and over again, you get all the complicated stuff that we know is in our universe. So let me give you a little example of something a little bit like that you can get here. So let me show you another one of these rules. Hold on, let me go up here, make it. Yes. I'm just going to show you another rule, same type. Let me do this. Okay. And oops, I should change that, shouldn't I? Okay. This rule is this is something yeah, I mean, I'm being challenged about sort of the kid appropriateness of this. This kind of thing of figuring out kind of what patterns you get by following rules. You really can do this. It's quite fun. You really can go and I particularly recommend this one here. It's very satisfying to do. You know, you're just saying every cell here, you just say, follow the rule here, decide what the color will be. Follow the rule here, decide what the color will be. And you might think it's not going to do anything very interesting. Keep following it a bit longer. You'll find, well, it does something a little bit complicated there. Let me, what I'm doing here is I'm starting it off from just one black dot at the beginning here. Let me start this off from just sort of a random arrangement of, let me try running this a bit longer here. Okay, well, actually, let's just look at this for a second. So the thing we see here is, again, at every black cell here followed the same rule that I talked about before. Everything's following exactly the same rule. And what you see, it's making this kind of complicated pattern. Let's try just running it a bit longer, see what kind of pattern it makes. Okay, isn't this incredibly weird? So there's this kind of background pattern it's making, and then there are these little things running around on top of that background. And remember, at every cell here, every dot here is following the exact same rule. So it's not like this structure here, this thing here had different rules. This thing here has the exact same rules. If we looked underneath, it would just be following, look at how the black and white cells are arranged, exact same rules as everywhere else. But yet, it kind of looks like we've got this sort of background here, and then we've got these things happening on the background. So remember my claim earlier about the universe, that the universe is just space, and things are happening, that everything we know about, electrons and all those kinds of things, are just sort of features of space. Well, this is very much the same kind of thing. Everything's not quite the same setup, not this thing with points and networks and things. It's a little bit different, but it's sort of the same idea, because we've just got black and white cells, in this case, little black and white dots, and the thing has, and even though the rule is always the same, we're still getting these things that are structured. So we might imagine, gosh, this thing here, that might be an electron moving along. It's not. It's just a sort of a toy version of that. But what's remarkable is that even though sort of everything is made in the same way, it seems there are different kinds of things here. And that's kind of what we think is happening in the actual universe. So this is the idea that the universe is just made of a bunch of points connected together. That's what makes space. Features of how those points are connected together, just like in this case here, are the things that make up matter, electrons, those kinds of things. Okay, so that's sort of the idea so if we were to look, down tiny, if we could do that, which we can't, but we can only do that as a theory, and then we have to work out the consequences of the theory, then we could figure out sort of what the universe is ultimately made of. Okay, so I told you a little bit about what space might be. I told you a little bit about what things like electrons might be. The next thing you might wonder about is, what is time? Okay, and actually, I've sort of already told you what time is, because I've said this network that represents space changes, and that progressive changing is the passage of time. So in this picture, which is not a network, it's simpler setup, what we've got is kind of space is going across the page and time is going down the page. What we had up here somewhere was these were sort of successive tiny, tiny moments of time that the network that represents space represents the universe. There's a really tiny universe here. The next moment of time, it turns into this and keeps going like that. So what is time then? Time, as I say, is just this progressive updating of the network that represents space and represents the universe. So in a sense, time is like the running of a computer, because what's happening here is sort of when we apply this rule, it's like we're running a computer program that says, take this thing and apply this rule that corresponds to a program and turn it into something like this. So we keep on doing that, we keep on doing that. And the process of doing it one step after the other, that is the progression of time. Okay, so people who so we've kind of got this idea. There's the universe. It might start from something, a very tiny network, and it gradually follows these rules. It grows, it grows, it grows. It has to grow a long way. Let's talk about some features of how it grows. So, for example, people are asking about black holes. Actually, in this model, there's something that's even blacker than a black hole. A black hole is something where stuff like light, anything can get into the black hole, but nothing can escape from it. In this model of the universe, there's actually something, you can have black holes, and I'll talk about how black holes work, but there's something sort of even blacker than a black hole, which is a piece of space can just disconnect. You can have this network, and a piece of the network just disconnects. And that means that if that happens, then there's no way to ever travel back from that disconnected piece. So you have the universe, and it's evolving, it's doing its thing, and it breaks off a piece, which is like another universe that can then also keep doing its thing, but it can never communicate with the first universe again. So that's one of the weird things that can happen in this model. I don't think that actually happens for our physical universe. It depends whether that happens in this model, depends on the rule one uses. So for example, this rule can't have little pieces that break off, but some rules can. So it's something that's conceivably possible for our actual universe. Okay, so let's talk about, okay, let me just show you to give you a sense of where we got to so far. So this is kind of a pictorial version of kind of the whole way that this theory of physics, theory of the universe works. We kind of are going down a little bit down the left-hand side here. We're kind of understanding a little bit how you go from the rule to this network. The network represents space. And if we want to know kind of, we want to know things like how far is it from, well, let me not get there. Okay, so that network represents space. The progressive application of these rules to make this network that represents space, that progressive application of rules corresponds to time. Now, what's all this stuff over here? Well, it gets a little bit more complicated. So in the history of physics, there are the fact that we can potentially make a fundamental theory of physics right now is a consequence of the fact that people have already figured out a lot of stuff about physics. So we only have to kind of go the last little bit. People have already figured out lots of things about how physics works. And the two big theories about how physics works are called general relativity and quantum mechanics. And both of these theories are about 100 years old, and they both have worked really well. What our theory does is to try and explain the foundations of why those theories work, and to try and explain sort of what's underneath those two theories. So relativity theory, invented by Albert Einstein, the original version in 1905, is a theory about space and time. What's called general relativity, invented in 1915, is a theory about gravity and space and time. And general relativity is the thing that predicted the existence of black holes, for example. and predicted the existence of gravity waves. And it's a very successful theory that talks about space and time and gravity. Okay, quantum mechanics is a theory about how things like electrons behave, not about what they're made of, but about how they behave. It's a theory which in some ways is much harder to understand than relativity. And it has a bunch of weird predictions about how there isn't just one thread of time in the universe. There are actually many threads of time in the universe. And it's been really confusing to understand how that works. In this theory of ours, we have an understanding of how that works. It's actually very, very cool. And this picture in the middle here is kind of representing the multiple threads of time that exist in quantum mechanics. The way it works, well, the thing that is from a kind of a sort of theory point of view, the thing that turns out to be sort of to me, one of the most exciting things about our theory is that it's been very difficult to make the theory of gravity, general relativity, fit together with quantum mechanics. And one of the things about our theory is that in our theory, at some level, general relativity and quantum mechanics are the same. They fit together perfectly because they're actually the same theory in a certain sense. So, okay. The people are asking all kinds of much more technical questions on this live stream, but let me keep going at a sort of more elementary level. If you want to know things like entanglement, please look at the website because there's lots of detail there about things like this. Yeah, lots of okay. So all right, where should I go next? I could explain relativity. I could try and explain a little bit of quantum mechanics. Let me try and explain. Okay, hold on. Let me just pull something up here. Sorry, hold on 1 second. I was unprepared here. Hold on a second. One moment. I think I might be able to prepare this. Oh, complicated code goes up on the screen, always a bad sign. But let's see if this will allow me to do what I want to do here. I'm hoping this will get me something that will be useful. Oh, questions here. All right, let me try and answer a few questions here. Okay, so a question here from Sanjeev, what are the points made of? The whole idea is they are the lowest level things in the universe. They're not made of anything. Everything is made of them, but they are not made of anything. You can think of them as completely abstract. They're a completely abstract construct. They are the points that everything is made of. Somebody's asking, so I'm going to just sort of unfairly kind of, I mean, what is energy in this model? Energy is actually the flux of causal edges through space-like hypersurfaces, which is an incomprehensible blob of stuff. But and there are questions here. Let's mention while I'm waiting for the thing that I'm trying to make work here. Let me deal with a few other things here. Gosh. Well, lots and lots of questions here. Entanglement. Well, actually, this thing called the branchial graph is a representation of quantum entanglement. Oh, I'm not getting what I wanted here. Let me see here. No, that's not what I wanted. Drat. Okay, well, I've got a plan B for how to do this. Oh, maybe. No, that's not what I wanted. Growl. No. That's why it took so long, but didn't give me what I wanted. Well, all right. Let's let me do this a different way. Sorry. Okay, I have another scheme for doing this. I'm just going to take pictures out of something that is on our website here. Let me find what I wanted to find. Well, all right. I'm going to try to explain to you, let's see. Hell, I wonder, this may be too hard. I was going to try and explain to you how special relativity works, which is the kind of Einstein's theory that relates space and time. It's very kind of elegant how it works in this model. Einstein sort of just set up special relativity as just assume things work this way. And then he derived many consequences from that. In this model, you can actually derive special relativity. So and you can derive things like one consequence of special relativity, one feature of special relativity is the relationship between mass and energy, the famous E=mc² formula. You can actually derive that in this model. You can actually work out why that's true. You can maybe I can give you some sense here of how relativity works. Okay, so it's a little bit complicated. What we're thinking about is when we apply the rule to our graph here, we're saying these red bits are the places where this rule got applied. So you're saying there is a piece of graph that looks like this, and then you can replace it with a piece of graph that looks like this. And where that piece of graph that looks like this is, you have to kind of find it in this picture, but you find it in a particular place, and then you will replace it with this other piece of graph that looks like that. So you can think about that just a minute. You can think about each of those little updates, each of those little ways in which the rule was applied. It's like an event. It's something happened in the universe. Okay, so all the time there are all these little events happening, all these little things that are like something happened. The rule got applied. Rule got applied. Rule got applied in all kinds of different places. You can apply the rule in lots of different places all around this network. Keep on applying it in all these different places, but there's an important and the question of you say this rule can apply in lots of different places on this network. So you might say, well, where do I actually do the rule? Where do I actually apply it? So this model says you can apply it anywhere you want, so long as the things that it is going to use in applying that rule are ready for it to be applied. What does that mean? Well, so here we've got a different version of this that's sort of a simpler case. Let me show it here. So what this is, instead of being networks, this is just just a second. I might be able to build this. Hold on one second. Let's just make something here. We might be able to do this. Okay, so instead of having networks, I've just got strings here, and the way this works is okay, there we go. This is going to work better. The way this works is that, okay, so let me show you. Yeah, that's a decent example. Okay, so this is a string of letters, B, B, A, A, et cetera, et cetera, et cetera. And now we have a rule. It's not one of our rules for networks. It's just a rule for letters. And the rule says whenever you see a BA, replace it with an AB, okay? And the yellow boxes are the events where something happened. So the rule is BA gets turned into AB, right? So this is showing which events we are choosing to apply at each step. We're saying this is every time we see BA, we replace it by AB. Okay, so if you think about it, if you keep doing that, every time you see BA, which is out of alphabetical order, you replace it by AB, which is in alphabetical order. Eventually, chunk, 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 you'll find that everything is in alphabetical order down here. Okay. Now, the thing is that you can, when you do that reordering, this is a particular way of doing that reordering, but here's another way of doing that reordering. Let's see, where is it? Okay. There's another way of doing that reordering where the particular A's and B's that you choose to reorder, it's a different set of A's and B's that you choose to reorder, but still at the end, you'll still have sorted it A's before B's. Okay, so these are two different choices. So the model, the theory says every time, it says it in the case of these graphs rather than the case of just strings of characters, but it says kind of every time you can apply the rule, you can consider applying the rule. But the only thing that it says for sure is you can't apply the rule to something unless the input to that rule is ready. Okay, what does that mean? That means that, let me try and lay something on top of one of these. Okay, what that's saying is this thing that's going to replace a BA with an AB, in order for one to be able to do that, the A that was here had already had to be processed by this event here. So it's like, it's not ready. It's not ready to have this rule applied. It's got to have this rule applied first. So this whole structure is called a causal graph. It represents the causal relationships. What can cause what? So if we start up here, we can't immediately do that event. We can't immediately do that rearrangement because this letter isn't ready yet. It's not, it had to have this event happen first. So we can think of this event being the cause of this event here. This event can't happen without that event there. So this thing here is this network. It's a completely different network from the network that we think represents space. This network here is the network of causes, the so-called causal network, the network that says what can happen, what can cause what. So what has to happen before what, okay? So this causal graph this maybe get too complicated, but I'll try it anyway. this causal graph is, okay, it says what affects what, okay? Okay, now here's where it starts to get a little bit funky. If we're trying to say, how does physics work? And we're trying to observe things in the physical universe, but we ourselves are in the physical universe. So whatever theory we have for how the physical universe works, it's also got to apply to us. And so when we say, we don't get to say, let's look at the universe from the outside and see what it's doing. We have to look at the universe from the inside, and we have the same rules applied to us that are applied to everything else in the universe. And in particular, if we have, if we are part of this whole story of rules getting applied and pieces of space and so on, then we are part of this causal graph. We are, so, you know, the thing where I'm thinking about what I'm going to do might be some very complicated version of a little piece of the causal graph down here. And the thing that I'm looking at, that I'm sort of thinking about or something, might be this part of the causal graph over here. But in the end, everything about the universe must be represented in this causal graph. And everything, so all of the pieces of what we're seeing in the world and all of the pieces of us must be part of this causal graph. And that has some very bizarre and interesting consequences. One consequence it has, well, there's one more thing I have to tell you, is that for many of the kinds of rules I can use, so long as things happen in the order that corresponds to this causal graph, it doesn't matter what order I do them in. So let me show you an example of that. So these are all different. If you look here, these events happened in different orders, different places. But all of them have the same causal graph, in the sense that they all have, the causal graph is drawn differently, but in terms of what, if we just look at what's connected to what, it's the same in all three of these cases. So let's see if I have an example here. I thought I had an example. Okay. Oops. What is that? Very bizarre. Okay. Let me try and find an example here. Here's an example. Yeah, it should be an example. Oh, come on. Well, so much for that. Okay, what about this? Well, okay. All right, let me make a comment here. So one of the things that's happening here, mentioned before, if you're like sorting the string, you can do it by just saying BA turns into AB, and you can do which place you say BA goes to AB, doesn't matter. There are different ways you can do that. So for instance, if you want to do it as quickly as possible, this is the way to sort that string as quickly as possible. You just use the BA, you know, use the rule as many times as possible here, as many times as possible here, and so on down the picture. But there are different ways to do it, and so this is a different way to sort the same thing. Okay, but I'm afraid this is getting a little complicated. But I just want to say that people are asking about relativity. One of the sort of big results of relativity theory is that time appears to run slower if you are traveling faster. And in fact, what you see here is exactly an example of time dilation, of time running slower if you're traveling faster. Essentially what's happening is this way of deciding what order to do these updates in corresponds to sort of choosing to do updates on this side before you do updates on this side, which is as if you're kind of traveling across this thing being here at first and there later. And so what you end up finding is the exact formulas of time dilation that happen in relativity theory. Okay, well, let me show you something maybe a little easier to understand. Let me show you something about how gravity works. So this is, I mean, one of the things that got talked about starting when relativity was started is this idea of space-time, the idea that space and time are somehow the same kind of thing. I don't think that idea is actually quite right, but these phenomena like time dilation come about because when you look on a sufficiently large scale in our model of the universe, it appears that space and time are similar. You know, I wonder if I'm going to be able to explain this. Let me try explaining a little bit about how gravity works. Okay, so in Einstein's theory of general relativity, gravity is all to do with curvature in space. Okay, so what is a straight line? Straight line, you know, we all kind of think we know what a straight line is. If we have a laser, for example, and we shine the laser somewhere, the beam of light from the laser will follow a straight line. Okay, so if we shine a laser a long way through kind of outer space or whatever, we think the laser beam will always just follow a straight line. Okay, so what Einstein claimed was that isn't always the case. So imagine that instead of having a laser, you know, we shine it through three-dimensional space. Imagine that we just are looking at at lines on a plane, for example, in 2 dimensions. So a line we can think of as being the shortest distance between 2 points. So, you know, take a piece of string, pull the 2 ends. If it just on a plane, you'll just get a straight line as the shortest distance between the 2 points. Okay, do the same thing on a sphere, and you don't find the same result. The shortest distance between 2 points on a sphere is the so-called great circle, which is something curved. Okay, so the idea that Einstein had is maybe everything, both light and just like a spacecraft that isn't firing its rocket engines or whatever, that's just sort of floating out in space, maybe all those things, they go on straight lines, except that space is curved, and the curvature of space is affected by the presence of mass. So in other words, if you have something like the sun or the earth, for example, the earth produces curvature in space, which means that what you thought was a straight line, it is a straight line, but it's a straight line in curved space, which means it's not something which is sort of geometrically a straight line, an ordinary straight line. And the curvature that Einstein said happens in space is exactly causes things to go in trajectories that are exactly the trajectories you get according to the law of gravity. So, for example, a trajectory of something going near the Earth might be something which is being, because of curvature in space as a result of the mass of the Earth, the sort of straight line in curved space might be something that corresponds to an orbit around the Earth. Okay, so that was Einstein's idea for how gravity works, that gravity is curvature in space produced by the presence of mass. And he said that he has an equation that says that whenever there's mass in somewhere, it produces curvature in space, and there's an equation that says how much curvature it produces, and that curvature will cause things to not go in ordinary straight lines, but in these curved lines that correspond to the effect of gravity. Okay, so it turns out that you can get exactly that kind of curvature in these networks that I'm talking about. So for example, think of a thing like this, or we can take all these different kinds of networks. Okay, let me show you this really weird one. So this is one where this is its rule. This is how it works. It grows itself. It starts from this, goes to this, blah, 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 keeps going, keeps going, keeps going. Eventually, it makes this weird thing here. So it's actually pretty regular, except for the fact that it is curved. It's a kind of a regular grid. It's kind of like you might say, well, this is just like kind of an ordinary piece of two-dimensional space, except actually it's curved two-dimensional space, like the surface of a sphere is curved two-dimensional space. So with these networks, it's possible to get space that is curved. And the space, remember, space is, all we know is what point in space is connected to what other points in space. But it turns out that when we have a very big collection of these points, sometimes they can behave like flat space, and sometimes they can behave like curved space. Okay, so the exciting thing is that the way that curvature gets made in these networks that make space is exactly the way that curvature gets made from mass in Einstein's theory of gravity. Well, when I say exactly, it's a very small scale version of that. When you look at it on a very big scale, when you look at this with trillions and trillions and trillions of points, then you get something which is just like what Einstein said should happen. When you look at it on a small scale, you see all kinds of complicated things going on. But when you just look on a large enough scale, it appears to just be following the standard laws of gravity. And by the way, when I drew those causal networks showing what causes what, there's sort of you can get these. This is another example of one of this what causes what networks. So the yellow dots are something happening in the universe, and the brown connections are that thing caused that thing, and so on. So this is the network of what caused what. I should say something about this, that the what causes what in the universe, something that happens right here now can't cause something that happens on the other side of the galaxy immediately. Why? Because the only way you can cause something, you have to, there's a limit to how quickly an effect can, something that takes only a certain time to happen can only correspond to going a certain distance in space. And that's a consequence of the fact of the speed of light. The speed of light is the fastest any effect can go in our universe. It's the fastest any object can go. It's the fastest any effect of something happening here can affect something happening somewhere else. And in these models, it's kind of the correspondence between this causal graph of what can cause what and how these events get laid out in ordinary space. It's the correspondence between those things that determines the speed of light. And in these networks, you can kind of see that there's this kind of cone of events that I probably got a better example of that. Here's a really simple example of that, where an event here can't affect, you can think of these events as being laid out potentially in time going down and space going across. So this event here can cause this event here, but this event here can't cause this event here. There hasn't been time for the effect of that event to reach this one here. So this event can cause this kind of triangle, this cone of events underneath it. The analog of that in theory of relativity is called a light cone. It's the region that a light signal, if you have a flash here, that the effect of that flash has a consequence for things that are a certain, as the light propagates out, it can affect things that are a certain distance. To reach a certain distance, you have to wait a certain time. And the distance that it goes, the distance that the sort of information can propagate, the distance the signal goes, is determined by the speed of light. Okay, so so that's just one feature of these of what happens in these models, as happens in relativity theory, is the fastest anything can travel is the speed of light. Now, I just will mention, very important concept in physics is energy. There are different forms of energy. There's like kinetic energy, energy associated with motion. There's energy associated with chemicals, chemical energy, all sorts of different kinds of energy. Well, it turns out one of the things that was sort of discovered 150 years ago or so now is that there's a uniform kind of thing that we can think of as energy. And energy can be in the form of heat. It can be in the form of things moving, can be in different forms, but they're all interconvertible. And there's a sort of a total amount of energy. And if you have a system that's all sort of closed off, the total amount of energy in it is always conserved. It always stays the same. So, okay, bizarre fact. So in our models, we actually know what energy is. It is actually if we look at, if we kind of slice this by having slices that say each one of these slices we can think of as being sort of one moment in time going by. So between one slice and the next, it's kind of like one moment in time going down the page. So bizarre claim in this model is that the number of causal edges that cross one of these moments in time is the amount of energy in that part of the universe. And so this is kind of a very abstract thing, but this is telling one sort of what energy is in this model. And so what happens is in Einstein's claim that, well, first claim of Einstein's is that energy and mass are equivalent. That's something we're able to derive in this model. Then the next claim is that mass produces gravity. Well, it turns out that that this identification of what energy or mass is exactly, it's a little bit complicated to see, but the effects here are what produce basically produce curvature in the network that corresponds to space in exactly the way that Einstein's theory of gravity says it should work. So that's pretty cool, since basically nobody's ever been able to derive that before, and we're deriving it from this very sort of kind of at least structurally simple thing underneath. I might mention black holes, for example. So what is a black hole? A black hole is typically a collapsed star in which so by the way, okay, so throw an object up or launch a rocket, make it go up into outer space. If the rocket has to go above a particular speed in order to escape from the gravity of the Earth. So for the Earth, it's 25,000 miles an hour. If you throw something upwards at more than 25,000 miles an hour, it will just keep going. It will not fall back to Earth again. If you throw it at more than 100,000 miles an hour, it will escape from the solar system, and it won't be pulled back by the gravity of the sun. If you throw it at more than 1,000,000 miles an hour, it will escape from the gravity of our galaxy. So there's this idea of escape velocity. How fast do you have to throw something to have it not be pulled back by the force of gravity? So it turns out that it's possible to have so much mass in a particular place, it produces so much gravity that the escape velocity is more than the speed of light. And that means that since nothing can go faster than the speed of light, even nothing can escape from the gravity of that thing. Instead, so that means even light trying to escape won't be able to do it. And so that means that since no light can escape, when there's no light, something looks black. And that's why black holes are called black holes, because they're things where there's so much mass in a small region of space that even light can't escape. Nothing can escape from them. Okay, so what in our model, I can show you kind of what a black hole, it doesn't look very exciting here actually, but this is what a black hole is in our model. It's a separation in the causal graph. Okay, what does this mean? Well, remember, the causal graph is saying what can cause what. So this is saying over here, this can cause this, and everything's kind of connected. And anything here can eventually cause something over here, et cetera, et cetera, et cetera. But over here, this is separated. There's nothing in this area here can ever cause something in this area here. And this thing here is basically like a black hole. In fact, it is mathematically a black hole, because what's happening is that things inside here, nothing can get out to cause anything over here. So you can't ever get anything, maybe some light or something like that, out from this thing here to cause something over here. And so what happens is, in this theory of ours, it's possible for, just as a result of the rules being applied to this graph that represents space, to end up with sort of chains of what causes what that separate like this, and that corresponds to the formation of a black hole. So, okay, there are all kinds of sophisticated things being said here. So I talked about whether energy is conserved. Okay, let me tell you a footnote to the energy is conserved thing. So one important fact about our universe is that it's expanding, and that was a fact discovered in the 1920s. And we know that the edge of the universe is basically expanding at essentially the speed of light. And our universe has been expanding ever since it started, probably 14.6 billion years ago. The law of the conservation of energy that they would teach in high school physics is true, but for one little exception. Actually, there are two kinds of exceptions, but one kind of exception is, except in the case of the whole universe, except for the expansion of the universe. It's not true there. It's not true, actually, in the theory of gravity. It's not quite true. But in any case, that's an exception to the law of the conservation of energy. And what you're seeing here, when there are more sort of causal edges down at the bottom of this, that's essentially the way in which energy is not conserved, corresponding to the expansion of the universe. Okay, so gosh, lots of questions here. Oh gosh, let's see. I can try and take a few of these questions, or I could talk a little bit. Let me just let me maybe just mention, this is, it's sort of crazy to try and do this, but I might do it anyway. Just mention how quantum mechanics works. Maybe this is totally crazy, but I'm going to try it anyway. Okay, so the difference between, so ordinary mechanics, stuff you learn in high school physics, is all about saying things like, you throw a ball, it follows a certain trajectory. Ball goes in a definite place, okay? That's classical mechanics. Quantum mechanics says, the usual mathematical theory of quantum mechanics says, well, actually, think about, instead of a ball, have it be an electron, just because it's smaller and quantum mechanics applies more to that. Throw this electron, instead of it just following a definite path, there will be many possible paths it could follow. And in some sense, it tries all of those paths. And what you get to see at the end is just the result of some mathematical combination of certain probabilities associated with those different paths. So quantum mechanics says there in a sense isn't a single thread of time. There isn't a single thing that happens. Instead, there's all these things happening in parallel. And what quantum mechanics typically is sort of quoted as saying is, and you don't know which thing actually happened. All you know is the probability that different things happened. Okay? Well, turns out in our way of setting things up, the thing that happens is, remember these ways of updating this network that is space. Well, it turns out that there are always many different ways that those updates could occur. This is showing a particular sequence of updates, but there are actually many different places and many different orderings of those updates. And it turns out that what we think quantum mechanics is the fact that there are many, many different orderings, and they're all kind of, they can all happen. And so this network here represents kind of, you start from this initial graph, and then after the first step, there's only one possible event, one possible update that can happen. Next step, there are 3 updates that can happen. And the idea is to follow all of these paths, okay? So in a sense, the universe is being very inefficient because it's following all these paths. But this very important fact is that we think that there could be all these different paths and it could branch out and there could be zillions of different paths. But we think that actually there's an important principle that causes these paths to often recombine. And in fact, sort of in the end, all the paths will have recombined. And that recombination is associated with a property we call causal invariance. That recombination is what lets one basically think that definite things happen in the world. Because otherwise, you might think from the sort of this quantum mechanical, there are all these different paths of things that can happen. You might think, gosh, how come anything definite ever happens? You might think, well, just there are all these different possibilities and they are all happening. Why does anything definite seem to happen? Okay, it's a little bit like the case that I mentioned before about relativity and things. The weird thing is that we are trying to see what's going on in the world, but we are also one of these weird branching things. And so when you say, what do we as a weird branching thing perceive about what the rest of the universe as a weird branching thing does, that's a complicated story, but we can sort of unravel that story by using some mathematical ideas and realize that the unraveling with this thing called causal invariance is what lets us know that we can have the we perceive definite things to happen. So quantum mechanics is associated with all of this branching, but because we are represented by this branching thing as well, that's why we don't perceive the branching. We still perceive definite things to happen, more or less. I'm simplifying quite a lot, but that's more or less the idea. And one of the things that happens is that there's this notion of entanglement in quantum mechanics. There's this notion of entanglement is sort of a representation of all these parallel things that can happen together. So you can kind of make a map of all the parallel things that can happen together. We call it a branchial graph because it represents sort of the effect of all these branches. Okay, so here's the super weird fact. So I talked about space being this network of joins points together. So we think quantum mechanics is associated with this, the kind of the analog of well, that there's also this idea of okay, roughly what's happening is that there are many different copies of the network that corresponds to space, and there are relationships between those different copies that are represented by this branchial graph, and those relationships represent the kinds of things that happen in quantum mechanics. That's kind of complicated, but sort of there are some mathematical principles of quantum mechanics, and those essentially correspond to questions about what straight lines are like in this branchial space, in this space where the different things in that space are, well, what are usually called quantum states, and where instead of moving from one place in physical space to another, you're moving from one place in branchial space, in the space of quantum states. It's really quite abstract, to another. But it turns out that the theory of gravity that applies in physical space, there's an analog, we think, of that theory that applies in branchial space. And the totally funky thing, if you're into mathematical physics, this is really an exciting thing, is that the laws of quantum mechanics, particularly a thing called the path integral of quantum mechanics, basically is the same law as kind of Einstein's law about gravity. It's the same law, but applied not to ordinary physical space, but to this weird branchial space that represents relationships not between positions in physical space, but between different possibilities in quantum mechanics. So, okay, just to say some really funky things there, you might have heard of quantum computers. All of this has lots to say about how quantum computers can work. And we talked about how black holes are these places where you sort of can't get an effect out of this region of space. There's sort of there's a speed of light constraint that says nothing can get out of this black hole. It turns out to make a quantum computer, you have to make the analog of a black hole, but in branchial space. You have to make something where the effect of this quantum effect can't get out of this region of quantum space, basically. And so, in a sense, when you're trying to make a qubit in a quantum computer, you're trying to construct a branchial black hole. Not the same as a black hole in physical space, but it's a different, weird, sort of abstract kind of thing that operates in this weird kind of space. Well, so that was sort of a sketch. I mean, what I've covered is sort of at some level, I mean, this is an absurd span of kind of sophisticated physics that I've tried to give a somewhat elementary explanation of. To really make the connections with physics as we know it, you have to kind of do all the fancy math and so on. But this is sort of, I hope, some sketch of what's happened. So I just try and answer a few questions here on the live stream. So Visit is saying, so gravity is like adding more space to space. Yes, that is correct. That's basically what it is. Oh, somebody is pointing out that the mouse pointer is too small. Okay, good thought. We should note that for the future. Is there some kind of limitation on the number of events that can happen at one time? Well, that's a little complicated because the notion of what you, an observer, as an observer, can only be sensitive to events that happen, to certain events. So for you as an observer, only a certain number of events can seem to happen at one time. The question of what you count as being one time is sort of arbitrary to the observer. It's a little bit complicated. It has to do with the theory of reference frames in relativity, which has an analog in our setup. Let's see. Well, there's a statement here, everything is energy. Not really quite in our model. In our model, everything is space, and energy has to do with the events that happen in space. Essentially, energy is related to the density of events that are happening in space. Energy is the change of things in space. So it's not space, the sort of things correspond to things about the structure of space. Energy corresponds to the change of the structure of space. let's see, there's a comment here, escape velocity greater than the speed of light, tachyons. Yeah, tachyons, that's the name that's given to the theoretical things that might go faster than light. In our theory, there aren't tachyons. They just can't exist. Let's see. Okay, there's a comment here. Black holes still cause the curvature of space that causes light to bend, even if, yeah. Okay, so I was eliding a lot of things there. When I was talking about the causal graph, the effect, that's a good question, actually. I mean, it's at a mathematical level, it's not difficult to understand what goes on. Gosh. Not super easy to describe that. Let's see. There's a question here, does an electron have a speed we can measure? Sure. One feature of quantum mechanics, well, okay, I was going to get into the thing called the uncertainty principle in quantum mechanics, which has a very beautiful analog in our theory. But let me not get into that. Okay, well, seems like we've come to the end of our time here, and I would encourage, if you're interested, I have tried to more advanced. If you look on our website here at this announcement post of mine, this has kind of a fairly non-technical description of how all of this works. I just started yesterday making my attempt to write a really elementary description of how this works. And I think I've been encouraged by this live stream to finish that, and I can send it out. And maybe we sent out a preliminary version of it on the chat here. So this is, we're very excited about kind of this theory, because I think it's the first time there's really been a way of deriving a lot of these facts about the universe that physics has shown us seem to be true, about how gravity works, how quantum mechanics works, equivalence of mass and energy, all these kinds of things. It's really neat to be able to derive those from a sort of lower level structure. We don't yet know, I've shown you some sort of sample rules that grow forms of space and so on. We don't yet know what the actual rule that might grow the actual space that exists in our actual universe is. And that's something we are super interested to be looking for. And we've been trying to figure out ways to approach trying to work out what that rule might be. And for example, we don't yet know a rule that will give us space being three-dimensional. We know rules that will give us space being other weird numbers of dimensions, but not necessarily three. So we could, another time, we can maybe talk about, we could do a more of a Q&A here, and we could talk about things like the beginning of the universe in this model, and the fact that the universe may have started infinite dimensional and only gradually become three-dimensional over the course of time. And we can talk about other kinds of things like that. But I think we should wrap it up here. So thanks for coming, and hope this was interesting. And if you want to learn more, check out the website and come to another Q&A. Maybe I'll do a Q&A about science in general, and more questions about this theory of physics in particular. Okay, thanks a lot. Bye.